The stereochemical outcome of the SN2 reaction is closely tied to the mechanism of the reaction. Last time when we talked about the general mechanism for the SN2 reaction, we mentioned that the reaction proceeds through the backside attack of the nucleophile onto the sp3 hybridized carbon, which then eliminates the leaving group, proceeding through the transition state, which is characterized by this pentagonal carbon, where the three groups that were originally attached to the carbon are now in the same plane, and they're attached to this half bond to leaving group X. And then finally the collapse of this transition state gives us our nucleophile attached to the carbon plus the leaving group X minus. And what is apparent here is that while we start with one configuration on the carbon center here, through this flat transition state, configuration inverts into the other enantiomer. And this is the so-called Walden inversion. And it's a clear connection between the mechanism and the stereochemistry of the reaction. So SN2 reactions proceed with stereochemistry inversion. Stereochemical inversion. And sometimes that inversion is very obvious. If we have, I think that's typically the case in cyclic systems. So if we have the cis bromomethyl cyclopentane, an attack of a nucleophile, say iodine, on the bromide-bearing carbon will expel the carbon atom and will attach iodine onto the opposite side. So now we will start with a cis isomer and we'll end up with a trans isomer of the product. And this reaction is an example of a stereospecific reaction. Which means that different stereoisomers of the starting material will give us different stereoisomers of the product. Stereospecific reactions are very useful in synthesis because they proceed with full control of stereochemistry, and that is something that we've seen as important. And that's why SN2 reaction is actually a reaction commonly used in preparations where stereochemical integrity of the product is important.